So what fun is knowing that there's all this energy lying around trapped up in matter if you can't take advantage of trying to extract it and put it to something more useful, or what we might consider useful. I suppose rocks enjoy being rocks, but I would rather them power my toaster. So, a few things we have to sort of take care of is the idea of isotopes. Perhaps you've heard this word before. So in chemistry, you would have talked about the things in the periodic table. For example, lithium or carbon. And what makes lithium a lithium is that it has 3 protons in its core. So if I were to draw that, it looks like this. 3 protons. And it does not actually look like that, but here we go. Carbon contains 6 protons. Put them in there for you. 2, 3, 4, 5, 6. Okay. Now, what's interesting about material is that, well, before we get into that, so all of chemistry has to do with electron exchange. And the number of electrons that an atom has to share is determined by the number of protons that are there. A lithium can hold 3 electrons because it has 3 protons to match them with. Carbon can hold 6 because it has 6 protons. And if lithium and carbon were to exchange some electrons, you could bind them. We'll stay out of the chemistry of it. I don't want to confuse things. But deep inside that nucleus, there's more stuff. There's not just protons. There are also neutrons. And so in the most common lithium, inside that nucleus, there are 3 protons and 1 neutron, which means that there are a total of 4 particles in there. Now, the mass of a neutron and a proton are approximately the same. So this thing here, it has 3 protons, but it acts like a 4-particle or 4-mass particle, because there are 4 things of approximately the same mass inside of its guts. So lithium-4, that's what we call that, lithium-4. Is stable. It hangs around that atom, the nucleus here, sticks together, and it doesn't tend to fly apart. In order to make carbon not fly apart, you need to put in 6 extra neutrons. For some reasons. Something to do with the strong and weak nuclear force, which we're not going to talk about, and you can learn more about at university. Good times. So this thing here, if it has 6 protons, which we've noted, and it has 6 neutrons, that's 12 particles in total. So this thing here would be called carbon-12. And this is the most common stable element or stable isotope of carbon. The next one up, carbon-13, so C13-6. That thing there has 6 protons. You can see in the notation there. And it has 13 particles in its nucleus. So if 6 of those 13 are protons, then 7 must be neutrons. This one is also stable. If you add 1 more neutron to that pile, you get carbon-14, which still has 6 protons. You notice that all the carbons have 6 protons, right? That means that they all have 6 electrons, which means they all behave chemically essentially the same. But this one has 8 neutrons inside of its nucleus. And so this one, for whatever reason, there's too many neutrons in this, this becomes unstable. So that means it's going to break down, and it can break down in a few different ways. It can either eject an bunch of stuff, some protons and neutrons, or it can break apart in a spectacular fashion, just like split in half or split and disintegrate. Or it can flip a neutron into a proton, thus eliminating an electron from it. We'll get to that more in the next section. But whatever it's going to do, at some point in time, this atom of carbon is going to stop being an atom of carbon, and it's going to release some energy. So we would call that radioactivity. Now this little carbon here, carbon-14, is the one that is measured when you hear about radiocarbon dating. So these kind of carbons are made through interactions with the surface of Earth and gamma radiation and all sorts of other stuff. So there's a certain percentage of carbon-14 on the surface of Earth, and it's perpetually being regenerated by a numerous set of natural phenomena. But if you take something and it has a certain amount of carbon-14 in it, and you bury it, and you isolate it from the surface where all that gamma radiation and recirculation is happening, those carbon-14s are trapped in that object, and because they're unstable, they start to break down. So if you dig up a skeleton or a chunk of wood or something that's very full of carbon, usually biological materials that have been fossilized, and you count the number of carbon-14s that are in them, if they have half the number of carbon-14 as something on the surface would have, then you know that, or you can assume that, approximately one half-life of carbon-14 has gone by, and so you can infer when that particular object was buried based on what percentage of the original carbon-14 remains. Now you should have done some half-life stuff in grade 11 and in advanced functions, so I'm going to stay away from it for now because I don't want to muck up the works. I just wanted these things up here to give you an idea of what isotopes meant and how to read them. Okay, so what does this have to do with fission and fusion and energy and physics? Well, we're going to park an isotope of uranium up here, uranium-238. U-238. Okay, so if you looked up uranium on the periodic table, you would find that it is element number 92. That means it has 92 protons inside of its nucleus. And because it's U-238, that means it is a 238 particle nucleus. So that thing then has 92 protons, and the balance are all neutrons. So let's see, 238, take out 92, gives me 146 neutrons. Okay, lovely. So if you were to go and measure the mass of that thing, and you can Wikipedia this just to make sure I'm getting the right numbers. The mass of this thing is 3.975448816 times 10 to the negative 25 kilograms per atom. Okay. So here's what I'm going to do. 92 protons can be divided exactly in half, and 146 neutrons can be divided exactly in half. And so what I would end up with is a particle that has half as many particles, so that would be 119, and half of 92 is 46. So I've got a thing here that has 46 protons, and half of 146 would be 73. 73 neutrons, 46 and 73 adds up to 119. Excellent. So if you scan to atom number 46 in the periodic table, you will end up with Pb, palladium. And this particular palladium would be PD119, palladium 119. Okay. So, this uranium breaks into, if I split it in half, 2 of these, and all of the bits are accounted for. So let me just write that up there. U238 has the same number of bits, as 2 palladium 119. Okay. So, if I were to go to Wikipedia and look up the mass of palladium 119 and double it, I would get, let's see, 3.948244725 times 10 to the negative 25 kilograms. So, if you take 46 protons, 73 neutrons, and pack them together, they weigh this much. If you take 92 protons and 146 neutrons, which should be the same number of particles, and you add them together, you get this much. And if you check, this number is bigger than this one is. If you configure them this way, they are heavier than if you configure them this way, twice. So if you were to take these bits, take that uranium atom, grab one half and the other half, rip it in half, and then measure the mass of what you have left over, some of it has disappeared. So question number 1, how much of it has disappeared? So I'm going to take this and this, and I'm going to subtract them. So 3.975444816 times 10 to the negative 25, subtract 3.948244725 gives me 2.72091 times 10 to the negative 27 kilograms. I am short that much mass. Well, where did it go? Well, the idea here is that making these atoms, making these nuclei that are heavier and heavier and heavier, you had to put some energy in order to make them stick. And that energy that you use to make it stick is released when you unstick them. So this missing mass here, missing mass, ends up being converted directly into energy because you've let it go through this E equals mc squared thing. So 2.720091 times 10 to the negative 27. Speed of light squared is 3 times 10 to the 8 squared. Let's see what we get. So that number, 2.720091 is 10 to the negative 27 times 9 times 10 to the 16 gives me 2.44800819 times 10 to the negative 10 joules. 0.24 nanojoules. 0.245 nanojoules. That is not a lot of energy. But please keep in mind that this amount of energy is also from a single atom, just one. So if you're taking chemistry, you should know that we don't do things an atom at a time. The standard unit for a grouping of atoms is a mole. So 1 mole is 6.022 times 10 to the 23 atoms. That's Avogadro's number. So if I took this amount of energy here per atom and I multiplied it by this, I would get the amount of energy per mole. So I take that times 6.022 times 10 to the 23. I get 1.474 times 10 to the 14 joules per mole. Now we're talking. So in a metric prefix then, this number 1.474 would be 147.4 times 10 to the 12, and a 10 to the 12 is a 10 to the 3 is kilo, 10 to the 6 is mega, 10 to the 9 is giga, then we have a tera. So these are 147.4 terajoules per mole. Okay, that's a lot of energy. And it's especially a lot of energy when you consider why we use mole for this number. If you count a mole of these atoms, then the amount of mass you have is this mass number, approximately, in grams. So 1 mole of uranium-238, if you could crack it in half like this, 238 grams of uranium-238 undergoing this process releases 147.4 terajoules of energy. 238 grams of fuel to get that. So just by comparison, I did a little research. In order to get this kind of energy out of coal, you have to burn about 4.5 tons of it. If you want to do it with wind power, there's quite a sizable wind farm near where we are in a place called Melanchthon, and that particular wind farm would have to run at maximum capacity for 8.5 days in order to spit out the kind of energy we're getting from 238 grams of nuclear fission fuel. Niagara Falls has a hydroelectric dam built on the Adlib generating station, and at its maximum capacity, it could pull off this amount of energy in 20 hours from 238 grams of fuel. So a nuclear fission facility, so it's a fission because I'm splitting something big into 2 smaller bits, produces an enormous amount of energy from almost no fuel, which is sort of neat. If you go back through that list of things, I mean, the hydroelectric dam, it produces a lot of electricity, and it's only by diverting water. So you've changed the amount of water that flows over Niagara Falls, which probably doesn't affect too many things. There's still some water flowing over Niagara Falls. The wind farm, that's okay. You're going to have to look at turbines, and I think they're a touch expensive to build, and you need hundreds, if not thousands of them in order to replace one of these facilities. The coal, you burn 4.5 tons of coal, and it ends up producing 4.5 tons of carbon dioxide, which is now up in the air, and we all have to breathe it in and or suffer the consequences of climate change. So this is a pretty good option. The other neat thing about this, the waste product, I don't know if you've got an image of nuclear waste in your head, but nuclear waste is stuff like this. It's metals. It is not a green liquid or slime or anything. It's metal. It's a solid state. So when uranium-238 is done in a reactor, what comes out the other side is, and let's not mince words here, it is frightfully dangerous, highly radioactive, but it's a rod. Right? It's no different in shape than this particular marker would be. So if you could figure out some place to put that so that the radiation isn't bothering anybody, then you've taken solid fuel, a very tiny amount of it, generated a reasonably tiny amount of solid waste, and then can store that solid waste someplace, and eventually over time, read millions of years, it will become inert on its own. So this idea of nuclear power, in fact, has sort of revolutionized electricity generation in North America anyway. Ontario generates most of its power by nuclear. New Brunswick does as well. France is a huge nuclear producer. And this is the basics of it. You've got some stuff. You break it into some other stuff. And then as a result of that, there will be some missing mass. And that mass is converted directly to energy, which your machine can absorb and use to boil water, which rises and then turns turbines, etc., etc. So I'm going to clean this off, and we're going to try this calculation but going the other way, doing a fusion instead of a fission. Okay, so we're going to start this off with deuterium, also known as hydrogen-2. So a hydrogen-2, hydrogens have one proton, and they have two. If it's hydrogen-2, it has two particles in its nucleus. So that's a proton is one of them, and then a single neutron is the other. If I took one of those things, and instead of subtracting them, or instead of splitting, I fuse them together, what I'd end up with is a particle that had two protons in its nucleus and a total of 4 particles. So that and that should give me this. And if you go and you look up the particle in the periodic table that has 2 protons, that's helium. And the helium that has 4 particles in its nucleus happens to be the most common isotope of helium, and it's stable. Okay, so if we try this calculation the other way around, I'm going to take the mass of deuterium, which was 3.340895 times 10 to the negative 27, and I'm going to double that because I have 2 of them here, and that's going to give me a total of 6.6868179 times 10 to the negative 27 kilograms. Then I'm going to look up the mass of a helium-4, and if I look up the mass of helium-4, I find that it has a mass of 6.6443214 times 10 to the negative 27. And you'll notice in that second digit again after the decimal, there's less energy tied up in a helium than there is in 2 hydrogens. So let's figure out what the missing mass is. I'm going to just take that 6.6868179. That's not good. 6.6868179, and subtract from it 6.6443214, and I end up with 4.24965 times 10 to the negative 29 kilograms, which is very tiny compared to what we had last time. Last time with the fission, we were short a 10 to the negative 27. So here we're short 100 times less, but it is less. So if you took this deuterium and you took that deuterium, you crushed them together to make a helium, a stable helium-4, this much mass has to be converted directly to energy via this exceptional machine. So 4.24965 times 10 to the negative 29, 3 times 10 to the 8 squared, gives me this number. Okay, times 9 times 10 to the 16 gives me 3.824685 times 10 to the negative 12 joules per fusion. So this is just accounting, right? The production of one helium requires 2 deuterium, and if you do that, each pair of deuterium you fuse releases 3.82, what is that? 10 to the minus 3 is milli, micro is 10 to the 6, nano, I don't remember what comes after nano. It's small. Some small amount of energy comes out. Okay? But again, from chemistry, we don't do things per fusion. We do them per mole. So I'm going to take this number here and multiply it by Avogadro's number. So that's times 6.022 times 10 to the 23. And I get 2.303 times 10 to the 12 joules. Okay, so that is 2.303 terajoules. Okay. So the production of 1 mole of helium through this process ends up releasing 2.3 terajoules. Now that is less than what we had from the fission, but it's comparable. It's in the right power of 10. But here's the difference. 2 moles of this is 4 grams of fuel. So if you could pull this off, 4 grams of deuterium is enough fuel to provide 2.3 terajoules of energy. Okay. Well, what comes out? Well, you get helium-4. The helium-4 is a stable isotope. That means it is not radioactive. It's helium, which is one of the noble gases, so it's inert. It doesn't react with anything. Helium is non-toxic, and you can demonstrate that it's non-toxic because it's also hilarious when you breathe it in from a party balloon. It makes your voice go all weird. So if you could flip this nuclear process around so that instead of fissioning heavy atoms, you were instead fusing lighter atoms, then this teeny tiny amount of fuel ends up producing a huge amount of energy with a waste product that we'd fill children's party balloons with on their birthdays. Now that's the holy grail, right? Could we get away with this? if you add into the fact that deuterium, right, like this exotic hydrogen, deuterium is, I looked this up, it's 0.0115% of all hydrogen. So that is not a lot, right? 1/100th of a percentage of all hydrogen. But you need to remember that hydrogen makes up 74% of all matter. So if I were to work that out, 0.0115 divided by 100 multiplied by 74 gives me 0.00851% of all matter. So just on average, if I were to take that number and I were to multiply it by your mass, 80 kilograms, I get my calculator failing, 80 kilograms times 0.00851. I end up with 0.0068 times 10 to the minus 3. So there's 6.8 milligrams of deuterium in your body right now. So if you were to go to a sizable body of water like Lake Huron, and you were to just start sucking up water and using electrolysis in order to split the hydrogens off of that water, then eventually this percentage of those hydrogens are deuterium. And in fact, the Bruce nuclear plant is built there because it's a can-do reactor and it requires heavy water. That's water where one of the hydrogens is one of these deuterium things. It requires it as a moderator. So they built it on Lake Huron so they could suck up and sort the water into water or to heavy water and not so heavy water. So the machines already exist to harvest heavy water from lake water. And there's a hell of a lot more than 80 kilograms of water in Lake Huron. So this fuel, not only does it produce an enormous amount of energy, has no waste products that are of consequence, but the fuel is literally lying everywhere around you, right? It surrounds us at all times. It's just waiting for us to grab it. So this is the future of energy production. If only it weren't so hard to do. It's not impossible. You can watch it happen in nature if you just look up, but do not look directly at the sun. This is what's happening inside of our star. It's made up primarily of hydrogen, and there's so much of it, and the gravity at the center of the star is so immense that deuterium sitting beside each other under gravitational pressure get crushed together so close that their nuclei fuse into a helium, and that produces this kind of energy per mole. So fusion is entirely possible. You just have to create a small star on the surface of the Earth within your power plant in order to make it work. So while you've got that buzzing around your brain, I think there is one scheduled to open in the next 5 to 10 years. Somewhere, I think it's in France. You should look it up, the experimental fusion reactor. That is intended to not just create fusion, which has been done at this point, but to create fusion in such a stable and reliable way that it produces more power than it consumes running the machine. So that reactor, if it's working, as of, check my watch, as of this recording, that machine is on the precipice of being able to produce commercial electricity, right? Electricity for sale, produced by thermonuclear fusion, which is awesome. So inside the problem set, there's just a bunch of atoms. You're either taking a heavy thing and splitting it, or you're taking two light things and fusing them in order to see what the missing mass is and then convert that to energy per mole. So